This is our video for task 12, so we're going to look at vector valued functions today. So what a vector valued function is imagine you have the component form of a vector is each of the parts are in terms of some parameter t. So we're saying that our first part is t squared, the second part is e to the t. Well, for each value of t, you would get a different component form vector. So like when t equals 0, you would get 0, comma 1. When t is 1, you'd get 1, comma e, and so forth. Imagine you plotted all of those possible component form vectors. You'd have tons of vectors coming from the origin. The path that would be created by the terminal points of those vectors, so at the arrowhead, if you trace that into a curve, that would be what a vector valued function is here. So say we had this, t squared e to the t. This red curve is all the different terminal points for different values of t. Now t is not necessarily representing time here. We could have negatives. So again, if you put 0 in, you'd have 0, 1. So notice that point's here. If you put 1 in, you'd have 1, comma e. If you put negative 1 in, you would have 1, comma 1 over e. So whatever 1 over 2.7-ish is. So that would be here. Now the arrows show the direction it's going. As t is getting bigger, we're going in this direction. So that's why we've got the arrows on there. So again, the vector valued function, the graph of it, it's all the terminal points, the tips of the arrowheads of all the possible component vectors based on this equation. Now the domain is the intersection of the domains of the two parts, because you couldn't have a terminal vector if for a t value that's not in one of the domains. So just to see that, so to find this domain, we'll first see what's the domain of the first part. Well, if you make t minus 1 greater than or equal to 0, because under a radical can't be negative, we get t is greater than or equal to 1. Doing a similar idea here, we need these t's to stay small, so t is less than or equal to 5. So just a visual, here's that t is less than or equal to 5, here's t is greater than or equal to 1. The intersection is the part that is in the domains of both those. So that would be when t is greater than or equal to 1 or less than or equal to 5. So that would be our domain for this vector valued function. If you want to sketch a graph of vector valued function, just pick some points and see what it starts to look like. So these have trig parts, so we'll pick our nice trig values. Cos of 0 is 1, so we get 2. Sine of 0 is 0, so we get 2, 0. Pi over 2 for cos is 0, so 0 for the first part. Pi over 2 for sine is 1, so we get negative 3. Likewise, if we kept going, we'd have negative 2, 0, 0, 3, 2, 0. So we'd go ahead and plot those. This would be our first point, second point, third point, fourth point, and then we're back. So then we put our arrowheads going that way. So it's important to note the order as you're plotting them as t is getting bigger, because that tells you how to put your arrowheads. Now, just something to note, you might recognize this kind of looks like an ellipse, and we can show you why it ends up as an ellipse. If we thought of the first part as our x part, that was 2 cos t, the y part's negative 3 sine t. Divide the 2 and the negative 3 over, and then use your Pythagorean property and substitute in, and we get something that should hopefully be familiar from last year. This is a equation of an ellipse because your radii is 2 for the x part, but 3 for the y part. All right, so vector value functions, you could have limits. So if you do the limit of an entire vector valued function, it's the same as doing the limit of each of the parts, the first part and the second part. So if we wanted the limit of this as it approaches 0, our limit of our first part, hopefully we recognize as that approaches 0, it's just 1. The limit of the second part, we could divide a t out of each of them, and then as t goes to 0, that part's just 2. So this is saying when t approaches 0, this vector value function should approach 1, 2 as a component form terminal point. Now, you won't actually have a point there on the graph, as you notice by this open circle, because when t would be 0, that's not part of the domain of either of those. So that's why there's an open circle there, but the limit allows us to see what it is approaching on the graph. And then the last thing for this video, continuity. Similar to domains, vector valued functions are continuous where both parts of the component function are continuous. So natural log is continuous for t is greater than 0. because our natural log graph looks something like that. Radical, we want to keep these t's small to make sure it's not negative, so t less than or equal to 6. So the overlap of t greater than 0 and t less than or equal to 6 would be when t is greater than 0 but less than or equal to 6. And a little more challenging one. So tan is continuous everywhere except for the odd pi's. So we could write that as t can't be pi over 2 plus pi n, where n's an integer. Because if you added on 1 pi to this, that would put us at 3 pi over 2. If you had 0 pi, that would just be pi over 2. Negative 1 pi here, that would be negative pi over 2. So this accounts for all of those. This one is all real numbers. So this would be where we are continuous. And you could write that in a way as saying it's on any interval from n pi over 2 plus or pi times n plus 2 over 2. Because if n was an integer, let's say n was 1, this would make it go from 3 pi over 2, and this would be starting at 1 pi over 2. So it basically goes from one odd pi to the next odd pi, and the reason the plus 2 is there is to get from one odd to the next odd, you've got to add 2.